Alright, so today we're going to be talking about the composition of functions. When we talk about the composition of functions, we're talking about the output of one function becoming the input of another. Now, we've worked with function composition before. Specifically today, we're going to be talking about the domain of our new functions. So with function composition, that's the output of one function becoming the input of the other. So we'll have to think about both the domain and the range as we start to work through these examples. So, given f of x, and then if we take g of x, if we were to say f composed with g, well, that would mean that g is going into f. So I'm taking the entire function g and all of those outputs, meaning our y values, the range, become the input in the argument for function f. This could be written with the same notation as f of g of x. And that's the first concept that we need to understand as we begin to work through these examples. So specifically, I said today we would be talking about the domain and range of a function. So the first example we're going to start with today is f of x equals the square root of x minus 8. G of x is going to be equal to 2x squared. First, let's talk about the domain and range of each function. Let us think about graphing function g first. So as you recall, g of x is equal to 2x squared. Now, we are taking function g and replacing the argument in function f. So if f of x is the square root of x minus 8, f of g of x can be written as taking all of function g and replacing the argument in function f. So we have the square root of 2x squared minus 8. It is not possible for us to take the square root of a negative number. So when we think about 2x squared minus 8, we only want to focus on the x values that return a positive value. If we were to graph 2x squared minus 8, that would be a shift of down 8 and a vertical stretch of 2. If we think about our x-intercepts, setting 2x squared minus 8 equal to 0, we would add 8 to both sides, divide by 2, and take the square root, and we would see that x is equal to plus or minus 2. So I have a positive 2, I have a negative 2 for my x-intercepts. The domain of function g, you'll see that that is a parabola, was negative infinity to positive infinity. But we've now created a new function where I'm taking all of the outputs of g and putting those into f. With that being said, I can't take the square root of a negative number. So all of these values are going to return negative function values. Meaning if I put in 0, 2 times 0 squared would be negative 8. I cannot evaluate this new function when x is equal to 0. So I am going to exclude all of those values. I'm looking to restrict the domain from negative infinity to negative 2, union negative 2, union 2 to infinity. So now I'm looking at this section of the function where the function values are greater than or equal to 0, and this part of the function where I have function values greater than or equal to 0. It's important that I include 2 and negative 2 because I can take the square root of 0. We do not need to simplify f of g of x any further. We have the square root of 2x squared minus 8 with the domain of negative infinity to negative 2, union 2 to infinity. For our second example, we will do g of f of x. So we have g of f of x, which we can write as g, and then showing that the function values of f become the input of function g. Now if you remember, f of x was equal to x minus 8, all under the square root sign. So we can write this as 2 times the square root of x minus 8 squared. So that is our function g of f of x. Now if we think about function f, follow my line down there, we can find that the domain is going to be 8 to infinity, because those will result in function values that are greater than or equal to 0. We cannot take the square root of a negative number. Now we can simplify this a little bit farther. If we are squaring the square root of x minus 8, those are going to cancel, and we're going to be left with 2 times x minus 8, which we can rewrite as 2x minus 16. So there is our new function, g of f of x. But remember, the domain that we put in for function f was 8 to infinity. Our composite function is linear. Linear functions have the domain of negative infinity to positive infinity. But I was not able to put in any values less than 8 for x in the original function. Because my domain was restricted to 8 to infinity for the first part, it cannot magically become part of the domain for the second function. So the domain of our composite function remains 8 to infinity because I was not able to put in values where x was less than 8 for function f. When we think about function f, the domain of that function is going to be from positive 8 to infinity. We can include the positive 8. Values less than 8 are going to give us a negative number underneath the radical. We are not looking at any imaginary solutions. 7 minus 8 would be the square root of negative 1. We can take the square root of 0, which is why we can include the 8. If we look at the domain of g, that is a quadratic function, so our domain is going to be negative infinity over positive infinity. Now the first thing we are going to find is f of g of x. In other words, we are taking function f and we are inserting the range from function g. Well, if we're talking about the range of g, and this is a parabola, then we need to start thinking about what that function would look like in terms of graphing. In our second example today, we will use f of x equals 1 over x plus 1. We will use g of x equals 3 over x minus 1. So there we have function f, we have function g. We are going to find f of g of x. And then we are also going to find g of f of x. We'll find the reverse of that flipped. We're going to find this first, where the function values of g become our input for function f. Let's talk about the domain first for g. If I have values that go in for g, then that domain has to be the same for function f. So for example, in function g, x cannot be equal to positive 1. 1 minus 1 is 0. That would make this function undefined. That's where we have a vertical asymptote. So our domain for function g, negative infinity to 1, union 1 to infinity. So now I'm going to take function g, and I'm going to replace that in the argument for f. So we will have 1 over 3 over x minus 1 plus 1. So I took all of function g, I replaced the x in function f, which gives me this function below. Now that's kind of an ugly way to leave that. I don't want to have a fraction in the denominator and then added to a constant, so I'm going to multiply both the numerator and the denominator by x minus 1. Now when I do this, I need to be careful and make sure that I'm distributing the 1 to the x and the minus 1, and that I am also distributing the x minus 1 to the first term and to the second term. So what this does is, in the numerator we are left with x minus 1 after our multiplication of 1. The x minus 1 is going to cancel out the denominator. We will be left with 3 plus 1 times x minus 1 is going to be x minus 1. We can combine like terms, x minus 1 over x plus 2. 3 minus 1 gives us 2. So what I did was I multiplied the numerator by x minus 1, the denominator by x minus 1, because this numerator and denominator being equal to one another is really multiplying this entire value by the value of positive 1. The x minus 1 cancels out the denominators, so I will just be left with 3, and then I distribute the 1 to the x minus 1, and I'm left with x minus 1. So this is our new function, f of g of x. In this function, x cannot be equal to negative 2. It would make this function undefined. That's where the denominator would be equal to 0. So our domain of f of g of x is negative infinity to negative 2, because negative 2 is not a part of our new function. Union, now this is where you need to be careful. It's not negative 2 to infinity, which is what you would think from this function. Remember, we had to exclude positive 1 from the original function g. So if it wasn't part of g, then positive 1 cannot be a part of the domain of function f. So negative 2 to 1, union 1 to infinity. And our last example for today will be g of f of x. We're going to use the same functions as before. So we are saying that we are putting function f, those function values, into function g. So it usually helps me just to think about it this way. I'm going to write the functions again just so that you have them. F of x is equal to 1 over x plus 1. And then g of x is equal to 3 over x minus 1. Now we're putting function f into function g. The value that we need to exclude from function function f is x equals negative 1. If x is equal to negative 1, that would make the denominator equal to 0. The function would be undefined. So our domain are all of the x values from negative infinity to negative 1 with a parenthesis, union negative 1 to infinity. I'm putting function f into the argument of g, so I can write this as 3 over 1 over x plus 1 minus 1. Now we need to simplify this. We don't like the x plus 1 that we currently have here in the denominator. So we are going to multiply both the numerator and the denominator by x plus 1. Remember to distribute that 3 to both terms, 3x plus 3 over. These are going to cancel nicely for us, and then I just have to distribute the negative 1. Remember, this 1 in the numerator does not go away. Although these canceled, when things cancel and simplify, you are left with a 1. Minus x minus 1. You are subtracting this entire quantity because it's negative 1 times x. Negative 1 times the positive 1. So this becomes 1 minus x minus 1. The 1's cancel. We have 3x plus 3 over a negative x. What value can we not have in the denominator? We cannot have x being equal to 0. You'll remember from the beginning, we also excluded negative 1. So x cannot be equal to 0 or negative 1 in our new composite function, which was g of f of x. So our new domain, negative infinity, negative 1, union, negative 1 to 0, union, 0 to positive infinity. And now you guys are masters at function composition.